Have you ever done something and someone else has taken credit for it? Isn't it the most uncomfortable feeling? Hi, my name is Tatiana, and today my team and I will be presenting our work on a model to classify cartoons and identify them using convolutional networks and autoencoders. You can pause the video here to see an outline of the presentation. Our project topics stem from a collective group interest towards cartoons and a desire to find a way to address copyright related to the misuse of these cartoons in the media. By using so many characters in memes and videos, some have become mainstream, and therefore the animation companies need to protect their cartoon characters from copyright violations. To tackle this problem, we decided to use a combination of CNNs and autoencoders to program an AI that can reliably identify said characters and images. The scope of our project is targeted to Disney cartoon classics such as Mickey, as the newer generation finds itself familiar with only the new characters. This project can be valuable to media companies as they will now have the ability to protect their characters from uncredited usage. Next, Daniel will present and explore the data we used.
Upon research, we found out that no dataset for cartoon characters expansive enough was available publicly. To avoid starting from scratch, we picked a small Kaggle dataset as a head start and expanded on it. We picked 12 characters total and downloaded 200 different pictures for each of them. A thorough cleaning process was carried to standardize the data. First, discarding low-resolution examples. Secondly, centering the image to focus on the character's features, mainly the face and body. Thirdly, resizing the image to a 224 by 224 shape. And finally, transforming the image to a JPEG. At the end, our first dataset had 250 pictures total, and we decided to train our first convolutional model with this. However, 250 pictures was too little for the model to properly learn features and get high enough accuracy for never seen data. To avoid a very time-demanding process to find new pictures, we took the route of data augmentation.
We began by applying 14 different filters to create 14 new copies of every image, therefore expanding our dataset without the need to find new images and edit the size again. To mass edit the images, we used Photoscape X, a photo editing software that enables you to batch edit, fix, and enhance photos.
Our first model was a simple convolutional network that incorporated the use of transfer learning from AlexNet. The AlexNet model was divided into two components. First is the neural network that is used to compute convolutional features. Secondly, a trainable linear classifier that takes these features as input. The diagram to the right shows the layers we used. The neural network component first has two convolutional layers, followed each with a max pooling layer. Then, three convolutional layers attached together with a max pooling layer at the end. The classifier contains three fully connected layers, with an output layer of 12 neurons for a total number of classes. After tuning the hyperparameters, we used a batch size of 250, learning rate of 0.01, and 21 epochs. With this model, the team achieved an insufficient accuracy of 85% on the validation dataset and 99% on training.
As seen previously, our primary model with AlexNet pre-trained weights was able to achieve a validation accuracy of 84%, which was insufficient for our model. One possible reason is that the AlexNet model is optimized for the ImageNet dataset, which consists mostly of real-life images. However, our dataset is entirely cartoon images, which are fundamentally different in terms of their color, texture, and edges. Our idea was to use transfer learning through autoencoders. Autoencoders are known to reconstruct images, and in the process they can learn valuable features and meaningful representations of images as they compress them down to a lower dimensional space. And the pre-trained weights from the encoder part of the autoencoder added with the classifier could form our feed-forward network to classify our images. As shown here, after performing the hyperparameter search on the convolutional autoencoder, we found out that the convolutional autoencoder gave best results with 30 epochs, a learning rate of 0.01, and a batch size of 512. However, as we came to realize, autoencoders require much more than 30 epochs to train, and academic literature showed that training them for a high number of epochs yields higher results. So using accelerated GPUs, we were able to train the autoencoder for 1000 epochs, and as shown, this was the best result we could achieve. However, these results were still not satisfactory. And as seen in the training curve, the autoencoder achieved a maximum validation accuracy of only 46%. Therefore, after experimenting with the autoencoder, the team decided to use the AlexNet pre-trained weights, which maintained the complexity of the model without making the classification overly challenging.
On to the results. At the end of image augmentation, we had over 30,000 images to work with. Unfortunately, due to limited RAM and computational resources, we had to reduce the size of our dataset down to 12,000 images over 12 characters. Despite this limitation, the model did extremely well. Our final validation accuracy came out to 97.5%. Now we will perform a demonstration of our model. Here are the images that we will demonstrate with. All 12 characters appear in these images, and most of the images have been augmented from the original images. Augmentations include image rotations, blurring, and color manipulation like grayscaling and brightness changes. Also, none of these images have been shown to the model until this moment. And here's the moment of truth. So as we see here, almost all of the images are correctly identified.